Good evening.
Right. Good evening, everyone. Great. Welcome to Space Oddities. My name is Bernard. I will be your host tonight. And as usual, we are a collection of amateur and professional astronomers who discuss about everything about space on a weekly basis. And we do this through the stream of YouTube. And as we do so, we talk about every topic from distant galaxies to nearby planetary objects. Tonight we're a bit short on the ground, but not as that short. So we normally have a few more guests. I'm sorry, a few more panelists. But that's absolutely fine because we have lots of content for you guys. First of all, I'd like to welcome the new people who are going to be viewing us tonight, and as well as the viewers who have been following us throughout the last few weeks. Don't forget to subscribe or to like, because that will definitely help us move forward and get more noticed on the YouTube algorithms. So we will start tonight by I'm going to start tonight by, I don't know what's going on with me tonight. Sorry, folks. I think I'm a bit tired tonight. We're going to start tonight by talking to Andy, because I think Andy would like to share with us some of his some of the content he's been putting on the channel recently.
Yes, thanks, Bernard. Well, I was just going to say, if you're new here, you may not realize that the Live Monday show, this show, is not the only content that we have on our channel. If you're new here, you may not realize that we started all working together on the now defunct global radio station, Astro Radio. And we produce a lot of programs about everything, literally everything under the sun on Astro Radio. And Daz, to my left or my right, depending which way you're looking at him, Daz and I are embarking on a project to edit those radio programs and to upload them to the channel. So do have a look around our channel, as well as the old Astro Radio programs. We've got a number of different series that we're putting together, different videos, and we've got a lot more in the pipeline. We've got a lot of plans that we've been discussing recently. We hope to introduce some new elements into this live show very soon. And but just basically, you know, if you've got a spare couple of minutes, just have a wander around the playlists in the channel, and you'll see what we've been producing. And of course, if there's anything you would particularly like to see on the channel, by all means, suggest it in the live chat here, or you can always write it in the comments, of course, after the live stream has ended tonight. But we are very, very grateful for any feedback, suggestions, views that you have, because we always say that this is your channel as much as it is ours. So we would really love to hear your suggestions and comments and feedback and insults and death notes and, you know, ransom notes and things like this. So anything you want to say, please don't hesitate to put it in the live chat or the comments after the show. So that's it, really. So back to you, Bernard.
Thank you so much, Andy. Yeah, and another good point, of course, is if you have any questions throughout the show, as we're going to, go through different content, please don't hesitate to post those questions on the YouTube comment section. We will definitely pick it up and answer it live. So there we go. Great. Well, folks, tonight, unfortunately, Roger has had some technical issues. So Roger will not be able to present what's in the night sky throughout the week. But that's fine, because we actually have some really good feedback from an event that took place during the weekend. So we're going to go to Steve. Steve, it seems like you went to some type of festival. Can you tell more?
Indeed. Thanks, Bernard. I'm the one who wants to be an amateur astronomer when I grow up. So I'm just going to hopefully hope you've got that on screen, and I'm just going to go into slide mode, and I'll make you all considerably smaller so it's not distracting me. Thank you. Ready to go. Yeah, what I thought I'd do, just bring together two items in a short item tonight, two things that we mentioned in last week's show. One was the parallelogram mount for binoculars, which Daz mentioned, and another I gave a brief preview of the Blue Dot Festival, which is held has resumed after COVID this last weekend. So this actually pulls the two together. First of all, the parallelogram mount. Here's mine. I acquired one a few years ago at my observing spot at the end of my garden. Over the brick wall there, you can see where the barley is. That's what I call my field of view. Haha. And the parallelogram, yeah, there you go. I had to throw something in. The parallelogram mount, you can see, oh, beg your pardon, gone too far. It's basically two hinged bars over on the right there on a standard tripod mount. It swivels around the standard tripod mount. On the left-hand side is the counterweight bar with the counterweight on, and a tennis ball on the end, which is very effective at stopping people bumping into the end of the bar in the hours of darkness, even though it's a bit inelegant. And on the right-hand end is where you would normally put binoculars. It was initially designed and constructed for mounting heavy binoculars, those that are too heavy to hold still at arm's length. I use it for a telescope as well. In fact, that is my solar scope for solar observing during the day, but it can be put a conventional telescope at night at times at night. And the mount there actually swivels left and right. You can swivel the telescope around a pin on the right-hand edge there by about 270 degrees. But the particular advantage of the parallelogram mount is that a bit like an angle poised lamp, those of you that remember the classic design of the angle poised lamp, it will hinge up and down and stay parallel. So if I just show you the view at its maximum vertical extent, and that is the angle that the telescope is at, even when you drop it down, as long as you just simply drop it down completely vertically, which is very easy to do, it will go right down at the same level, but still be pointing at exactly the same object. And this is, I find, really good for outreach purposes, which is why I acquired it. You can show to a parent one moment and drop it straight down to show their youngster, who would be equally interested in just within a second or so. Now, this is what we did at the Blue Dot Festival this last weekend. I was there with my astronomy group, Mac Astro, on the Friday, Macclesfield Astronomical Society. Here I am using the parallelogram mount and the solar scope somebody's actually observing, because on the Friday we did get 4 or 5 brief glimpses for about 10 minutes of the sun, and people were really excited to observe. But the rest of the weekend, the Friday and Saturday, unfortunately, were a washout. And if you're wondering what that framework is at the back of the view there, it is in fact the Lovell telescope at Jodrell Bank, the first of its kind in the world, the first steerable radio dish in the world. And there it is with us at our observing location down on the right hand side. It's a glorious thing, 65 years old, 76 meters across, and completely fully steerable. It was amazing, an amazing piece of invention, an amazing piece of innovative engineering in its day, and still is. Now, the reason I find it really useful for outreach is this is the last festival before COVID happened. It can be used completely inclusively, so that people in wheelchairs can get a direct view in the eyepiece just as anyone else would, which without any special arrangements, which is quite unusual for some mounts. This was a photo taken by one of our members, my friend and member Sue Scott, a couple of years ago. So, of course, the Blue Dot Festival is a 3-day festival of science talks and music combined, and a lot of science presentations, lots of fun for kids. And here we are on the Friday night when Groove Armada were there. They turned the dish round to have a light display. This is the stage sets there where the main talks are given, as well as the music acts. There's just a few of these images taken by another of my colleagues at Macastro, David Tolliday, who actually a few years ago won the newcomer prize in the Astrophotographer of the Year award with a star trailing image. there's the Lovell telescope on the left, the main stage set, and some blue dot and the whole crowd. I think we're going to have a briefing on this tomorrow, but I think they were expecting about 30,000 people on site. Mogwai, the group Mogwai, were on Saturday night, and in fact Björk from Iceland, of course, performed with the Halley Orchestra on the Sunday night. And I'll finish with that lovely image of the sun, which I think is a solar dynamics observatory image of the sun projected onto the glorious Lovell dish.
Wow.
And some of you may have noticed when I'm on the YouTube channel here on Astro Radio, behind me I have a painting that I did a few years ago of the Lovell dish, and there it is, just a quick glimpse of it.
You did that, Steve? That's amazing.
The presentation. So I'll just stop the screen share. And the only other thing, personally, my two highlights were I had a few nice off-the-cuff words with Tim Peake when he was in our staff and speaker hospitality area over lunch, which was really nice. And the other highlight, I breathed deeply. No, it's not working now. Was this badge, the James Webb Space Telescope badge? It's a golden badge of the mirror array, and I can there. Hopefully you can see it glinting every once in a while. We all covet these. They didn't have that many, but we went to the James Webb Space Telescope stand, and a few of the staff got them, of which I'm really proud. I hope it doesn't taint, because it's glorious.
How much you want for that, Steve?
I'll see.
Saw it first.
If I can get some more, I will send you some, but they're quite precious.
Super cool. Super cool.
Back to you then, Bernard.
Thanks, Steve. I mean, those were really great images. How did they manage to project images on that dish? I was wondering.
I was going to ask the same question. They must have had a hugely tall tower.
Yeah.
They have the. I think this was the 6th year that the festival has taken place, and they have developed it year on year on year. And so I think they have developed their own light show, basically. And honestly, I don't know exactly how they do it, but they've even had artworks projected onto the dish in previous years as well, a whole moving art composition, as it were, with the telescope. And in fact, this time they were observing pulsars during the whole of the festival, quite unusually. Whether or not the data would be suitable is uncertain, because of course there are 30,000 mobile phone devices that were completely okay to use. During for the festival event, they allow that, of course, for the public. But during normal operation, it's a radio quiet zone on the Jodrell site. We all have to have our phones off or on flight mode, so there isn't the slightest disturbance to the science that goes on.
Oh, so the advantage of that being a radio telescope and not bothering with cloud, you had a radio cloud covering the dish itself. Space Barnes Productions in the chat says great painting, Steve.
Oh, that's very kind. Thank you.
Yeah.
Thank you.
I agree. Looks really nice.
It's lovely. It's great. I wish I could paint like that. I can't even draw the curtains. So,
Can I ask another question? You obviously, science is great, but you obviously also, witnessed some great concerts. Who really struck you as a great show to be at?
Well, here I have an admission to make. Because I was on staff on 12-hour shifts, by the time it got to the music, I had actually gone home just to get some rest for the next day. So I really wanted to see Groove Armada. I'm quite a fan of Groove Armada.
Sure.
And I really wanted to see Björk as well. But I'm sure there will be reviews of the music from those that were there. Some of my colleagues did stay, and it's always a really good event. I'd commend it to anybody, especially as a family occasion. It really amazes me how many families go around with buggies, little children, and they're entertained for the whole weekend. It's a great place to be, and it was really nice to see people enjoying themselves normally, just as it used to be just 2 or 3 years ago. It was a really great event.
Yeah, cool. Well, I think it shows how passionate we are as astronomers, that you decided to, to be on that stage, not on the stage, but to be at the event for 12 hours, and then couldn't go for the music.
Well, I'm Jodrell staff at weekends, so I had no option. But it was a really enjoyable, strenuous, but really, really enjoyable event. I would not have been there. It's brilliant.
Yeah, that's so cool. I'm sure there's going to be videos on YouTube of the show anyway and all the rest. So super cool. I'm definitely going to think of going next year. That's definitely for sure.
Let me know if you do.
Yeah, take my daughter there. I'd love to. Cool. Well done. Very good. Thank you so much for sharing that. Why don't we go to Keith now? Because I think Keith has some things to show to us today. And as a reminder to all our viewers, don't forget, if you have any questions, please submit them to the chat box.
Okay, folks, I'll just share my screen, hopefully. Let's try that now. Hopefully, can everyone see that okay?
Yep.
Yeah.
Yes.
Right. Fantastic. Okay. I'm on rocks tonight, so there's no maths, so everyone can stop panicking straight away. What I'm going to talk about is a particular rock called Basalt, and basically it's a dark-coloured volcanic rock, and we see it actually on more than just the Earth. It's also seen on other planets in space, and we'll talk about it now. But let's do a few basics before we start. The thing about rocks is they get recycled. So rocks can be converted from one form to another. And this big diagram here shows what's called the rock cycle, where, for example, an igneous rock can be weathered away and turned into sediment, the sediment compressed into a sedimentary rock, and then maybe squeezed more into a metamorphic rock, and then ultimately it might melt, and then you're back to an igneous rock again, and you can go round and round and round in this cycle. Now on Earth, this rock cycle has effectively destroyed the first 600 million years of Earth history. There are no rocks surviving that are more than 4 billion years old, or at least none that we've found anyway so far, because they've all been recycled into new rocks. And by the way, because of that recycling, that's why we don't see a lot of craters on the Earth's surface. It's not just that the atmosphere burns up smaller impacting objects, but the earliest part of solar system history, when there was a lot of cratering going on, that would have included the Earth, but the Earth has wiped off the evidence due to the rock cycle, so we don't see very much. Note one thing though, and that is that the production of sedimentary rocks requires an atmosphere. So if you've got a body in space that doesn't have an atmosphere, then that part of the rock cycle will be missing. Okay, next thing is, and this diagram might be a bit smaller on the screens, but don't worry, because I'm only going to focus on one bit of it. Geologists classify igneous rocks in various ways, but the two main ways that they do it is in terms of the amount of silicon dioxide the rock contains, and also the size of the crystals in the rock when it solidifies. And basalt actually has a low silica content, hence the fact it's over on the right-hand side of the diagram here. It's called a mafic rock. And it's also consists of very fine crystals, because what happens is that basalt cools down very quickly because it's erupted onto the surface of a planet, cools quickly, so the crystals are small. If, on the other hand, that magma that created the basalt had been left underground to cool slowly, you would have had much bigger crystals. Okay, so basalt is both low silica and has small crystals in it. Too small, more often than not, to be seen with the naked eye. Well, here's a few pictures of basalts, which I took the other day. They're from my collection in the shed. On the left-hand side there is a very typical basalt, in that it's dark in color because it contains a lot of minerals which contain iron and magnesium. And sometimes, though, that same basalt can have holes in it, as you see on the right-hand side there. And these holes, which are called vesicles, are actually gas bubble holes. When the magma is erupted to the surface, it brings up with it a gas content. And as the lava pours out, the gas bubbles expand inside the lava, creating these cavities that you see in the picture here. Now, by far and away, the most abundant gas is actually steam. It's water vapor. And indeed, the water in the oceans originated from volcanic eruptions. Here are a couple more basalts, and I'll go through these pretty quickly. The one on the left is another basalt with gas bubble holes in, but they've been filled up with mineral. And the same thing on the right. But on the right, there's an additional thing there you can see, which is that, in fact, the rock is a sort of reddish color. And that's because it has been altered, it's been oxidized, and the iron in the rock has turned to partly to iron oxide, which you can see in the color there. And that's a dead giveaway that there's a lot of iron and indeed magnesium in these mafic igneous rocks like basalt. Now, the trouble with basalt, as you saw in those pictures there, is apart from the holes, if you get them at all, it's a very, very fine rock. The crystals are tiny. And so it's really very difficult to see anything with the naked eye. So back in the 19th century, German geologists came up with a solution. Basically, you cut a sliver off the rock, you glue it to a microscope slide, you grind it down until it's only 0.03 of a millimeter thick. And when it's that thin, by the way, light can shine through the minerals. They're translucent or even transparent. And what you have then is called a thin section. And that can be placed under a microscope. And once it's under the microscope, you can use polarizing filters to tease out details in the minerals. And you see in this picture here that this picture of a basalt contains these minerals with stripes running through them. And that's a mineral called feldspar, which is an aluminium silicate. And then we've got other minerals which are brightly colored, such as pyroxene and olivine, and those are iron magnesium silicates. And this kind of subtle information can be found, as I say, using thin section petrology, which is what we're seeing a picture of here. This is, by the way, a basalt from Earth. There's nothing terribly unusual about that. Okay, well, can we see basalt in space? Well, every time we look at the moon, we're looking at it. The mare, the oceans on the moon, are areas of basalt lava, which has emerged from the interior and spread out over the surface in a liquid form. And it's often filled up old craters. So Mare Crisium, top right of the moon there, you can see it's quite clearly a circular shape because that was a huge impact crater that's been filled up with the basalt. The basalt is lying on top of older rocks beneath, which are paler in color. They're called anorthosites, and I'm not going to bother to talk about those today. Now, these mare, these basalt flows, formed round about 3 billion years ago. So about 1,500 million years after the moon was originally formed. And that's what you're seeing there. And of course, they create fairly smooth regions on the moon, which is why, of course, when Apollo 11 went to the moon, they landed on the Sea of Tranquility, because being covered in lava as it was fairly smooth and a relatively safe area to land a lunar module on. It's fairly flat. Okay. Moving on. So what do lunar basalts look like? Well, there's a lump of basalt there on the left, which is from the moon. That's one from Apollo 17. It's a bit pale looking, but I suspect the picture's a little bit overexposed, to be honest with you. And you can actually see it has got gas bubble holes in it, vesicles. Actually, that's not very typical of lunar basalts. Usually they don't have vesicles because there's not much gas in them, but that one does. And then on the right-hand side there, we can see a thin section of a basalt sample taken by on the Apollo 11 mission. And you can see once again, the same minerals we saw on the Earth example there. That very, very large, deep blue thing there is pyroxene crystal. This light blue one here is an olivine crystal, and you can see these needle-shaped feldspar crystals as well, mixed in with the rest. So it's broadly similar to an Earth-type basalt. By the way, how do we know that if we're looking at a basalt sample, it really comes from the moon? Well, one of the first things is that, in fact, actually, because there's virtually no water in basalt from the moon, the mineralogy of the rocks is fairly simple. And if you plot their aluminium, their iron, and their magnesium content, they tend to plot along a very, very distinct line, that line with all the blue rectangles on it. Whereas on Earth, because there is water vapor in the rocks, you get a much more complicated chemistry, and Earth-based basalts plot all over the place, as you can see those little grey specks on the same graph. And another thing, what you find on the moon, of course, is that these basalt rocks have been subjected to further bombardment by objects coming from space. So you find in the basalt, you'll find there are cracks running through due to impacting objects. And indeed, some of the minerals have been melted by the heat created by the collisions. And that picture down the bottom left there shows a partly melted olivine crystal surrounded by fractures, as you can see in the rock there. That is typical of a lunar basalt. You would not see that on a basalt from Earth. That, by the way, is another microscope slide picture. And of course, we see basalt on Mars. On the left-hand side here, we've got a picture taken by the Spirit rover. These are, again, pieces of basalt, that characteristic grey-black colour. Again, vesicular, you can see gas bubble holes in them. So there was water content in the basalts on Mars, whereas, as I said, on the moon, that's pretty rare. And these lumps of detached basalt are lying on the surface of Mars, where wind erosion has started to ablate the surfaces, creating these concave features on the outside. So that is a close-up of some pieces of basalt on Mars. But then, of course, also, some of the largest features on the Martian surface are also made of basalt. Basalt is a low viscosity lava. And when it erupts from a volcano, it can spread over a large area. And in fact, in Britain, for example, there are huge areas covered in basalt, such as the northern end of the island of Mull, and quite a bit of the Isle of Skye as well, up in Scotland. And also, don't forget that basalt is incredibly abundant on Earth, on the ocean floor. Virtually the entire ocean floor of the world is covered in basalt, and that's approximately 70% of the Earth's surface. On Mars, we see shield volcanoes created by the eruption of basalt. And those are what we're seeing here on the right-hand side, including the biggest one here, Olympus Mons. Olympus Mons, that shield volcano, is so big it virtually covered the whole of France. That will give you an idea of the scale. But you'll also notice something else about them. They're quite squat. They have very gently sloping sides. And that's because basalt runs away very easily. And therefore, you get a very flat-looking volcano, a shield volcano, as a result. So there we go, folks. Some examples of basalt on Earth, on the moon, on Mars, and indeed how the hell you can sell one from another using what's called thin section petrology. And that is the end of that. Thank you very much.
Thank you very much, Keith. I'm right in saying, aren't I, that the Giant's Causeway in Ireland is formed of columns of basalt?
Yes, I'm sorry, yeah, I forgot to mention the biggest area of basalt of all in the UK, because it's the Antrim Plateau, which includes the Giant's Causeway. Absolutely right, yeah.
Because when it cools, I think I'm right in saying if it cools suddenly, it fractures into sort of hexagonal shapes. Yeah, because where I live, of course, it's an intensely volcanic area, although the last volcanoes erupted about 10 million years ago, and the basalt is just everywhere. So the other thing I want to point out about basalt is that it's an incredibly hard rock. And I know this because I stumbled onto a sheet of basalt and I snapped my femur. So in a battle with my femur against a lump of basalt, the basalt won. And I will never do that again because that was just an awful experience.
Yeah, I think also another amazing place is Fingal's Cave, is it?
Yes, that's on the island of Stafford.
And that's on this. I think it's on the same fault line as the Giant's Causeway. And well, it's so big you can actually sail into it. You can climb out, and they actually sometimes have concerts inside. But it's these very big. It's very tall. It's cathedral-like, and you've got these big pillars of basalt. Pillars there, and it is a really spectacular sight.
Well, the other thing that I hope to point out to you when you come over in October is that our Roman baths in the village, one of the walls, they've used these hexagonal features from the basalt as a feature. So they're very clever, the Romans, the way they've actually done that. But you know, they were good at things like that. The whole wall is just sort of made up of these roughly hexagonal shapes of basalt.
I'll quickly say something about. Sorry, I'm just going to leap in here because people are probably wondering why you get hexagonal column shapes. If you actually look carefully, you'll find that they form the cracks, the hexagonal cracks, form at right angles to the cooling surfaces of sheets of lava or intrusions in the ground, and they're caused by the rock shrinking because obviously as it cools, it contracts, and that's why you get them. Yeah. Right. Sorry, I interrupted.
Yeah. Fantastic.
I just wanted to remind our audience that Andy lives in Spain, despite his accent, which is when he's talking about where his village is situated and all that. Actually, where exactly are you situated, Andy?
I've no idea. I'm in Catalonia, about 90 kilometers north of Barcelona, about 45 minutes from the French border.
Okay. I think Steve's got something to say.
Well, I forgive me if you've said this in your presentation, Keith, but am I right in thinking that the normal basalt, as I think you did say, is kind of more gentle flowing of effusive lava, whereas if there are the gas bubbles, the vesicles tend to be a much more eruptive, explosive volcano. Is that correct?
Right. Yeah, it's nearly right. The gas bubbles in basalt lava, you've often seen pictures like eruption, particularly in Hawaii, where you see bubbles literally bursting out the top of the magma, and also you see fountains of magma coming out of cracks in the ground. It's all driven by gas pressure, if you think about it, as much as anything else. But here's the thing, right? There are other types of lava like andesite and rhyolite and so on, and these are much more viscous than basalt. So when these get erupted from a volcano, as they start to cool, as they approach the surface of the volcano and erupt out, they solidify. And as a result of which, they plug the volcano up. It blocks itself up, basically. So then what happens, of course, is the pressure of rising magma inside the volcano is pushing against the stopper, if you like, of solidified magma. And the whole volcano then bulges outwards. The sides fall away more often than not, and you get a sideways blast, which is what happened with Mount St. Helens.
Yes, the whole side of the mountain blew out, didn't it? Yeah.
I think Daz has a question.
Well, it's in the chat. It's from Space Barnes Productions. It says, on the moon, is it possible to determine whether certain features were formed during the lunar night or the lunar day based upon the speed of cooling and the resulting differing structures of minerals?
Right. Okay, I've just found the text on the screen. Based on
That's a good question.
Well, it might be possible, but you've got to remember that basalt solidifies at around about 1,300 degrees Celsius, which is pretty hot. And I don't think the ambient temperature surrounding it would make much difference. I don't know. I could be wrong.
Yeah, see, the moon, when you can talk about the day side and the night side, of course, the temperatures are different. But what you've got to remember is the moon, when it first formed, was a lot closer. And they were both formed. We talked about this before. From the thinking is it was a massive collision, destroyed most of the Earth, and formed an accretion disk around the Earth, which a lot of the bigger chunks fell back to Earth, and the rest of it went on to make the moon. In fact, it is thought to it could maybe have also made two moons, which eventually merged together. But the closer side to the Earth, the side we always see, is actually thinner than the far side. So the far, but of course, also it was spinning faster at the time, and it was closer. And they think possibly some of this may be due to the fact that it was the day side, or what as you want to call it, or the side we always see, was facing the Earth. And of course, the Earth was a neighbor that was still very hot and very sticky and magma-ish. So it was radiating heat more, and this kept the near side more malleable. And this is why when it was hit by meteorites, when they collided with it, it would, of course, then, because that side's hotter, the crust is thinner, then of course it would melt the crust, and all the magma that was inside would then come up again. And of course, this is what we were saying, it would fill any craters that were formed by the actual collision and also spill out. Yes, so this is why also I could be wrong with this one, but I think that the crust on the far side, the rocks there are older than what are more on the crust is older than what is actually on the closest side, especially where the mare were.
Yeah, we need to establish something, which is that lunar highlands, as they're referred to in the Apollo missions, that paler grey coloured rock that you see, which is, a lot of it is an igneous rock called the Northite, was formed earlier than the basalts by a few 100 million years. And the thing is, and this is the thing, right? The moon was so hot that the entire surface melted all over to create that anorthosite, which is, comparatively speaking, a fairly low density igneous rock. And it's like the froth rising to the surface. As the moon melted, the whole surface was covered in this lighter, and I mean lighter in terms of density, igneous material. And then later on, the basalt was erupted from the interior and covered up some of that earlier highland terrain. By the way, this total resurfacing, as it's often referred to, it's quite possibly happened on Venus too, because one of the strange things about Venus is a very, very small number of craters, which suggests that, in fact, the surface has been melted and refrozen again after most of the original cratering occurred. Moreover, the distribution of craters on Venus is almost uniform all over. There are no bits with more and bits with less. It's like the whole surface is the same age. And if you remelted the whole surface of Venus, that's what you would get.
Yes, Steve.
Well, just on the back of that, actually, I think they reckon the surface of the Venus might only be about 700 million years old. It may have been resurfaced as recently as that. But I was going to say, I've actually found a photo showing some of the differential colours in the lunar basalts, actually, which I could throw up if needed in a minute. But I just think one of the real enigmas, in fact, one of the real enigmas in the whole solar system, is that as our listeners may know, the side that faces us, where all the lunar maria and all the basalts are, is radically different to the far side of the moon, which has got virtually none at all. And I think it's a huge puzzle as to why, and all the maria have been made by enormous impacts in the Imbrium period, particularly, and thereafter, why they've all occurred kind of on one side of the moon, and why that side of the moon is now the one that faces us. Because if that side faced us from the very early days, you'd have thought that Earth and its size would have protected that side of the moon from all the impact. So why did they all come from one direction, and why they've now orientated themselves towards us? I think it's a fascinating enigma. Can I just quickly... Sorry, Keith, you were going to say something.
No, just about to reinforce what you said. And if you look it up, ask the question on the internet, you get 5 or 6 different answers. Nobody really knows.
Real puzzle.
Yeah.
Shall I just quickly share that image?
Yeah, let's have a look.
Yeah.
Not a particularly good one, I have to say, but in fact, this is one of the first astro photographs I ever took. No, it isn't particularly good on screen, I can say even now. It was just completely by chance with a really old Canon camera. I just took a photo of the moon, but I hope you can see up here, there are clearly differential sort of more blue colours there and more brown colours in the lava here. I think one being more titanium rich and the other more iron rich, but I'm sure Keith will definitely know more about that. You can see distinctly sort of an indigo blue down there and a more sort of browny undercolour there. So
you have another intervening process here besides composition, and that's particle size on the surface. And so the longer that surface element has been around, the longer it's had to collect micrometeorite impacts. And so you may be looking at a deeper or more shallow dust on the surface, which would have different reflective properties.
Yeah, understood.
Yeah.
Incidentally,
I didn't mention it, but the titanium mineral in basalt is called ilmenite.
Ilmenite.
Yeah, and there's lots of it on the moon.
Great.
Keith, that's really good. I have actually a question. Why don't we just do a basalt session tonight? I have a question on the basalt. Basalt, sorry. How far away have we discovered basalt within our solar system? Obviously, we have to find them on volcanic planetary bodies. And yes, we talked about Venus, but I'm also thinking of, Io obviously is probably, we just haven't been able to send any spacecraft to study its surface. And it's probably, too hot there. I don't know. I'm just thinking, apart from Mars, the moon, and Venus, is there anywhere else where we have found basalt or
I'm going to be very, very cautious here. Because it's quite possible that it's on Mercury, but I don't know for sure. But the thing is that, as you know, when you get about halfway through the asteroid belt, the nature of the objects turns from essentially rocky bodies like Vesta to ice-covered bodies such as Ceres, and then out into Jupiter, you're then getting satellites which have got frozen ice surfaces, which may have been mobile in the past, as we know. But the thing is, we're no longer seeing rock on the surface, we're seeing ice. But going back to Vesta, if we go back into the solar system a bit, the large asteroid Vesta, there are rocks on Vesta, such as howardite and things like that. They've got fancy names. Chemically, they're very similar to basalt. And in fact, actually, the infrared spectrum that you can get from the surface of Vesta is a very close match to a lot of meteorites that land on the Earth's surface. We've got an awful lot of bits of Vesta amongst the world's meteorite collections.
Right. Great.
Great. Thank you.
Cool. Thank you so much. I thought that was really interesting and very informative.
Thanks for that, Keith.
Yeah, it's really good. Really good. Folks, to our audience, don't forget, if you have any other questions, please type them down on the comment section of this video. Great. We're not going to have an image section tonight. Unfortunately, Rachel has not been able to join us tonight, but please do send us these images. We do love seeing them. They were every week whenever we see new images from our audience. It's just great. I don't know, Andy or Daz, would you be able to send in the link as where our audience can submit images?
Yeah, we'll sort that out. We'll sort it out later. Yeah, we'll put it in the description at the end.
Yeah,
the end.
That would be great.
Send your images in. We love looking at them.
I can find it. I've got it here somewhere. I'll dig it later. Then
that's
you
cool.
are really talented out there.
Yeah, you really are. And also, not as Barnard said, the images we're getting, but also just any nightscapes or anything like that as well. Anything that you think's special to you, and it's got a story, then just pop it up, and just to sort of like mix it up a little bit. There's nothing that we won't put up. It's I should rephrase that. Should rephrase that. But yeah, we're happy to see your beginning shots, your end shots, everything.
So the end shots.
Yeah, we just want to encourage people to send stuff in, and we'll go through them, and you know, and maybe you may be even invited on to talk about your imaging. So just think something for the future. Watch this space.
Totally. Yeah, and when you submit images, don't forget to submit descriptions of maybe how you took it, why did you take it, and we'll more than happily share those images at our next session. Great. Cool. Why don't we go and say hello to Lou from the US. Lou also has something to share with us tonight.
All the way across the lake.
Yeah.
Oh, these this discussion of images. Kareem and I will be at Stellafane this coming weekend. One of the largest amateur astronomer telescope making conventions. So we're going to take a few images of some of the really creative telescopes people have made. Maybe we'll send a couple in.
Where is that? Where is that being hosted?
It's in Springfield, Vermont. Springfield, the most common city name in the country. You don't say the street after it, you have no idea where Springfield is.
Where the Simpsons live.
That's where I'm going.
I resisted.
I couldn't.
So today we're going to continue our series on exoplanet detection. And for those of you who have really hung in there with me and been watching the shows of each of our segments, you will, if you finish this, you will be extreme exoplanet experts, which sometimes only means you'll know one more thing than anyone else in the room, but nevertheless, you will know a lot about exoplanets. So let me get my screen shared here. Let's see. Let's do this one. There we go. And we'll start the slideshow, I think. There we go. Okay, does everybody see that?
Yep, got it.
Okay, good.
Yeah.
So this is the next segment in our series on exoplanet detection, and just to do a brief history of what we've learned. We started off. We started off with a history of thought of how far back can we identify philosophers and astronomers even thinking that there might be planets around other stars, but then we kind of segued into the first exoplanet detection, which was a planet orbiting a pulsar. And so we talked about how you might infer the existence of a planet around a pulsar by noticing the difference in the timings of that pulsar, because the planet is tugging that pulsar towards you and away from you. Then we talked about what's called a radial detection method of exoplanets. Remember, most of the methods that we're going to use are indirect methods. We're not, looking at the planet in most cases. So we use the analogy of a car headlight on a dark night in the distance, a mile away, and you put a grape near it. Well, you're not going to see that grape. So we look for indirect methods of detection. Radial detection method means that the planet orbiting the star is pulling the star close to you and away from you as the planet orbits. And we can see that in the star's spectrum, in the Doppler shifts of the star's spectrum. Then we talked about the transit detection method. This is where the planet is orbiting roughly in the plane that we're looking at the star. And so every time the planet comes around in front of the star, a little bit of the starlight dips out. So you see that characteristic in periodic dip. And so there we can infer the existence of a planet. So that's what we've done. Today, we're going to talk about astrometry. And if you ever go into the field of astrometry, you'll be an astrometrist. And I actually knew an astrometrist at Goddard Space Flight Center. These are people who measure the positions of things in the sky very accurately. So let's go to this slide. Now, last time I presented this slide, I haven't updated it. So I'm sure there are a few more detections, but this is good as of June 30th of this year. And this shows you kind of cumulatively how many detections of exoplanets have been made based on the method that was used to detect them. So down here in the red, you see radial velocity method has discovered a fair amount. Transit detection methods have discovered the huge amount, and so on. And then all the way down here, you see in the gray, astrometry. And even if you look very carefully, it's very hard to see any planets that have been discovered using astrometric techniques, which is not the planet moving the star towards you and away from you, but moving the star back and forth in front of your line of sight. Seems like a very obvious thing to do. Look for the change in position of the star because of the gravity of the planet tugging on it. But as we're going to see, it turns out that it's very difficult to do this. So here's what we got. We've got a planet orbiting a star. And in fact, we have a star orbiting a planet. They are orbiting their barycenter, which is their center of gravity. Sometimes, as in this animation, that barycenter, which is indicated by the plus sign, is actually inside the star. But no matter, they orbit each other. And so here you can see the star is pulled left and right, as well as front and back. And so we can, the goal is to detect that left-right movement, that astrometric displacement of the star. One of the advantages of this method, you might remember in the radial detection method and the transit detection method, you want to have planets orbiting roughly in your plane, your line of sight. But using this method, you don't have to have that. You can look perpendicular to the orbit and actually see the star moving left and right being displaced. So that's an advantage to this method. So here it is. Here's another graphic. We're sighting a star and looking at how far, we'll just say left or right, okay, how far displaced that star image is over time. And we're looking at the angle of that wobble. And that angle is very, very tiny. Remember, the closest star to us besides the sun is about 4.3 light years away, about 25 trillion miles. Sorry for you guys in the UK. You have to think about kilometers. I'll let my friends do the calculation there. So it's a very, very tiny angle, and that is why it's so difficult to do this and why we can only do it, use this method with the very closest stars. And the way it's done is they measure the movement in the star over time by finding 3 or more reference stars and measuring the distance of the star in question from those reference stars. And so as the star moves, the distances to each of those stars will vary, and then that would be a verifiable detection of an exoplanet. So I went to, we've talked about the NASA Exoplanet Archive. It's a great resource. And so I went to the NASA Exoplanet Archives and I asked the question, how many planets have been discovered using the astrometric detection method? And the answer is 1, maybe. This star, this exoplanet system, which was identified as an exoplanet system in 2013. The planet has a very easy to remember name. It's Dennis P J082303.1-491201B. And you'll remember that we talked about how we identify planets around other stars. The very first planet you discover around a star gets the letter B associated with it. And then the next planet, C and B and so on. So that's the planet. But it's kind of on the border between planet and brown dwarf. It has a mass of about 9,000 times the Earth, 28 Jovian masses, has an orbital period of 246 days. And this is important. It orbits about 0.36 AU from the sun, roughly the distance Mercury is from the sun. So it's very close, which means that star is going to experience its gravitational pull more strongly than if it was further away. Now that star is only 64 light years away. That's a long distance, but in terms of the cosmos, in terms of the kinds of distances that we're talking about, that's a relatively close star, and that's why an astrometric method will work on it. So there is only one detection using this. Now, having said that, there is a spacecraft the European Space Agency launched called Gaia. And Gaia's mission objective, should it choose to accept it, and it did, was to measure the positions of 1 billion stars very accurately in 3D, right? So 2D would be back and forth across your line of sight, or maybe up or down. And then the third dimension, depth, can be measured with Gaia's onboard spectrograph to get the Doppler shift movement of the star. I looked for it. I don't see any candidate detections of exoplanets yet from Gaia, but we are expecting, as they said in Harry Potter, we are expecting great things from Gaia. And so hopefully this number of astrometric detections will increase over time. Now, once again, just heralding the NASA exoplanet database. If you want to find out anything about exoplanets and how they're detected, go there. But today I'm going to show you another cool resource, and this is really a lot of fun. This is Eyes On. Eyes On. This is a JPL visual interactive product. They have Eyes on Earth, Eyes on Asteroids, Eyes on the Solar System, and Eyes on Exoplanets. So if you go to Eyes on Exoplanets and download it onto your system, you'll be able to go to any exoplanet system that has been discovered, and it will zoom in on this. It will show you what the planet might look like. It will show you the orbit of the planet or planets if it's a multiplanetary system, and you can rotate the image in 3D and play with it and have a lot of fun. So Eyes On is a fabulous resource if you want to know more about exoplanets. And I'll stop it there today. We'll continue the series next week.
Great, thanks, Lou. Really interesting.
Yeah,
very good. That's fun.
Totally. And thanks again for sharing those sites where we can access all this data. That's very, very useful.
I will put that in the description in case you miss it now. It will be after the live stream ends. It will be probably tomorrow in the description.
Thanks, Andy.
Great.
Cool. I'd like us to go back to Keith. Keith, you had something to clarify with us with regards to Basalt and Mercury.
Yeah, it turns out I just actually had a look at the information about Mercury, and strangely, there are no basalt flows on Mercury's surface. Apparently, the sluggish circulation of materials inside Mercury has prevented that from happening. So there's no Earth, Mars has been the principal places you're going to find these things. Yeah, and the picture behind me It was taken on the island of Staffa, which is where Fingal's cave is, that everyone's heard of. And that's columnar jointed basalt you can see behind me. If you ever go to Iona, which is a monastery, you know, right on the western end of Mull, Staffa's about 5 miles to the north of that.
I thought Mendelssohn made that up. I didn't know Fingal's cave was a real place.
Oh, he went there. He wrote the music after he'd been there. It was a tourist destination at the time. Yeah, yeah. You've got to drive across. You've got to get a ferry to Mull, drive all the way across Mull, get another ferry to Iona, and then you can get a boat from Iona to go to Staffa. And incidentally, not only Fingal's cave and the basalt, but there's some wonderful puffins there, if you know these little seabirds. And they're not scared of people at all. You can walk right up to them and I'll just look at you. It's quite strange, you know.
Yeah.
Cool. Well, thanks for that clarification, Keith. Let's move on to Andy. I think Andy has some stuff he'd like to share with us.
Yeah, news of a bizarre new discovery with regard to a fast radio burst. Now, let me just share my screen and I will talk to you about those just as a bit of background. So fast radio bursts are bursts of radio energy coming from all over the sky. And they are very, very short in duration. And they are literally all over the sky. And here's just a simulation of you know, just to show you that they're going off all the time, all over the sky at great distances. Now, typically they last for just a few milliseconds, but in terms of power output, they output in just 1 millisecond more energy than the sun does in 3 days. So these are incredibly powerful events. They were first detected in 2007, and since then, there have been well over 100 of them identified. We've only had the technology to detect these relatively recently. And the main reason is that although they are very, very powerful at the point of origin, by the time they reach the Earth, if you can imagine getting your mobile phone, taking it to the moon and sending a signal back to the Earth, the signal level is about 1,000 times weaker than that, 1,000 times weaker than a mobile phone signal would be from the distance of the moon. What are these things? Nobody knows exactly, although their properties seem to indicate that not just one astronomical phenomenon is responsible, one type of thing is responsible. There may well be multiple things that are responsible for these incredible fast radio bursts. And to detect them, we need telescopes like this. This is the Chime telescope in British Columbia in Canada. Now, since this came online a couple of years ago, it's really accelerated the rate at which these fast radio bursts are discovered. And it's being an amazing, amazing instrument. The main candidate for the origin of these fast radio bursts are pulsars, those rotating super dense remnants of the cores of stars and that flash like lighthouses, or an even more extreme form of a pulsar called a magnetar, which has the most intense magnetic fields in the universe and are quite bizarre. They're also very dangerous objects. If you got within about 1,000 miles of a magnetar, the atoms in your body would literally dissolve. So they're not nice. But these are incredibly magnetic pulsars or neutron stars, and they are the main candidate. In fact, we've only ever discovered one fast radio burst in our galaxy, and that came from a magnetar. And we've only discovered 28 magnetars. Astronomers have only discovered 28 magnetars so far. So they're not that common in the universe. But what I really want to talk about is a new type of fast radio burst that was detected recently by this Chime telescope. And let me just show you how bizarre it is. This is the signal. Instead of it lasting for just a few milliseconds, it lasted for 4 seconds, which makes it unique in terms of fast radio bursts. And as you can see, within this signal, there are lots of peaks. And apparently, if you were to listen to this, it would sound very much like the rhythmic pulsing of a heartbeat. There are not that many things in the universe that pulse rhythmically. And this is the first time something like this has been seen. And we really, really don't have an idea of the mechanism that is causing this FRB to pulse. But further studies will indicate, hopefully discover what it is. The vast majority, though, of fast radio bursts do not repeat. They flash for a few seconds, few milliseconds, and are gone forever. We never see them from that location again. A very small minority of fast radio bursts, they do repeat at fairly predictable intervals. This one, though, we don't know yet whether it's going to repeat. So whether we'll ever see it again is unknown at the moment. But whatever is producing this heartbeat-like signal must be something incredibly strange and bizarre that we either haven't seen before, or it's something like a pulsar or a magnetar exhibiting a behavior that we've never seen before. So there we are. So I just thought I'd keep you up to date with that. And if there's any news on this, if it does repeat, of course, I'll let you know here. So there we are.
Very interesting.
Thanks, Andy. I think we're soon going to have invaders coming to us. No, I mean, the only logical explanation, of course, is aliens doing this.
Of course it is. But I have to say, this signal comes from billions of light years away. It's extremely far off in the universe. So if it is aliens, they're going to take a hell of a long time.
Yeah, they're just telling us that they're on their way.
Too much.
Yeah.
So no. So
it's just a signal to say they're on their way.
Exactly. But what I find fascinating is that it could be indicating a completely new type of astronomical object that we've never seen before.
Yeah.
And that's the exciting thing about it. It may not be a pulsar, which we know about fairly, or a magnetar, which we sort of know about. It could be something altogether new in the universe that we haven't seen, that's exhibiting this sort of heartbeat-like behavior. Really, really interesting.
The pulses were not only increasing in their magnitude, but also compressing in their timescale as well.
Absolutely. Absolutely.
Yeah, really interesting.
Really interesting. Yeah. Yeah. Really, really strange signal. Nothing like it has ever been seen before. Let's hope it's one of those that do repeat.
Yeah, well, they're compressing because the aliens are coming towards us. Remember, blue shift.
Yes. Don't give up your day, Joe.
Just trying to put it out there, you know.
Maybe
I'm just wondering if it's a binary object, actually, and there's two things. You know, if it's a binary object, is that causing the pulsing?
That would have to be incredibly fast moving, though. If the total.
Well, we see weirder things with millisecond pulsars.
Never know.
Well, that's true. That's true. Yeah. But it doesn't appear to be any sort of eclipsing binary. It's something generating that
Very
4 second signal.
Watch this space.
What indeed?
Cool. Well, and yeah, do keep us posted on that, Andy. I think that's really exciting stuff. Folks, I know we've gone over the hour, but I think maybe Daz, do you want to?
No, mine's not time critical, so we can do it next week. And it's a bit of it's just a few little things that people might like to learn. That's all. So I can do it next week, no problem.
Yeah, no worries. I'll do mine as well next week. So there you have it. Thank you so much for tuning in and following us and listening to us. I hope you enjoyed the show and you've learned a lot. I certainly have learned some cool stuff about Basalt today and exoplanet detection. Please don't forget to subscribe and to like, because that definitely helps us with the algorithms and pushes our popularity. If you have any other questions about what we discussed tonight, please do leave a comment. We will pick up on the comment box and come back to you. Don't forget to send us the images and as well.
Yeah, I've posted Rachel's email in the thing for images. So just have a look in the YouTube chat, and it's at the bottom. So there, it's already there. So that's where to send your images.
Yeah, we love your images, so please do send them to us.
Yeah, and just before we finish,
yeah,
Lou, Kevin Earp is asking for a short presentation on the Stellarphane convention, if possible.
Oh, sure.
Yeah.
Glad
So,
to.
he says he's built scopes in the past and enjoyed the convention reviews and write-ups in Sky and Telescope mag years ago. So he'd love to see you present something about Stellarphane if you could.
Kareem and I will be there taking pictures and probably doing on-camera interviews.
Oh, fantastic. There you
have,
are, Kevin. You've got that to look forward to, mate.
Interesting things to show next week.
Yeah, fantastic.
Fantastic. Yeah.
Right. And hopefully next week we'll have our usual panelists, Rachel and Roger, to keep on improving the quality of this show as we do every single week.
Yeah, sorry if you're expecting to see your photo in the readers gallery tonight, but we will never forget about it, and we'll hold it over till next week.
Yeah, definitely. So that's it from us. So goodbye, panelists.
Goodbye, everybody. Don't forget
everyone.
to have a look around the other offerings on our channel. And any comments, feedback, or whatever, always welcome. So as I said, this is your channel as much as ours, and we look forward to seeing you next week.
Absolutely.
Have a fantastic week, everybody.
Thank you.
Take care. Bye-bye.
Bye-bye.
Goodbye.
Bye.
Bye now.